ladies and gentlemen. My name is Roberto Brighenti, I'm from Parma University. Today I'm going to talk about defect tolerance in a very strange class of materials which are completely different from what we have seen before. So that's the outline of my presentation. First, a brief introduction, the topic of soft matters, and then I will talk about the main mechanical aspect of small commerce, which I consider in experimental and numerical calculation. We use a statistical description of the chain length distribution, which is a classical tool to describe the mechanics of this kind of material. And finally, I'll show you a model to explain how this material behaves under large strain up to the final failure in presence of geometrical defects, such as notch or cracks. And I have some results and conclusion. So, it's well known as usually geometrical defects affect heavily the mechanical behavior component, and normally we have a lower strength capacity of structural component in presence of such discontinuities. Okay. However, if we consider another class of material, which are typically called soft materials, like polymers, elastomers, and so on, we have a completely different behavior because we don't notice such a strong influence of defects on the strength of the component made by this class of metals. So we can mention here, for example, colloids, polymers, foam gels, hydrogels, granular material, biological tissues, and so on. They are fully amorphous, and they are composed by many long polymeric chains which are linked together in some points, and so the mechanical behavior of this class of material comes mainly from the entropy effects then on the atomic bonding, as we usually notice in standard class of materials. So we have very long macromolecules which have a relative motion between them. We have, as I mentioned before, very high entropy-related effects. We have to take into account that all these long molecules, as I show later, are linked together by means of covalent cross-links junctions, and we have to take into account that by stretching this material, we have an increase of the mechanical internal energy, and at the same time a decrease of the entropy because of the more order that we can get to the structure. So this is a scheme of what we can observe by considering a polymer. We have a very long molecular chain. Normally we have many entangled chains which are linked together in several points that we call crosslinks. And if we observe what happened to the material when we stretch it, we have that all these chains become more aligned along the single direction, and they are stretched, so the elastic energy is mainly contained inside the single chains that change completely their initial conformation. So we have a decreasing of the entropy because of this geometrical phenomenon. So typically, this kind of material are described by the classical rubber elasticity theory that takes into account the probability distribution of the so-called R2R distance that describe the average distance between the crosslinks that exist between the polymeric chains. So this is a standard probability distribution that is used in this case, which is a Gaussian. We have several parameters: the number of segments that compose a single chain, the average distance between the two ends, and the standard deviation of the distribution of the chain segments. So this is the scheme of what we have for a single chain. For example, we have the length of each segment composing the chain, and the vector R that identifies the end-to-end distance of each single chain. So we have one cross-link here, for example, and the other one is in the other end of the chain. This is the distribution of such a vector R, and mainly the area below this curve represents the number of cross-links that are present in one unit volume of material. We can easily calculate the energy, the mechanical energy related to the stretch of the material by simply multiplying the increment of the entropy by the absolute temperature. And for example, if we consider simple stretching along the three directions x, y, and z, we have this expression here. And in general 3D elasticity, we have the mechanical energy psi, which is function of the deformation tensor f by this simple expression, where we have the Boltzmann constant K here, we have the absolute temperature, and the trace of FTF minus 3. So in general, if we want to calculate the mechanical energy for this class of material, we have just to consider all the contribution of all the chains involved in the stretch phenomenon. So we can integrate the energy of one single chain, and we can obtain the energy of the whole volume of material that we are considering. So we have the distribution of the chain length phi and the energy for one single chain. So in practice we are adding up all the contribution by using this expression. And finally, this is the standard Gaussian distribution which is used for polymers, where we have all the parameters I mentioned before explicitly written here. So the energy per unit volume can be easily obtained by integrating the above expression. We can have a final equation that gives us the value of the energy per unit volume, and that depends, of course, only on the deformation tensor F that we are applying to the material. If we are considering an incompressible material, as typically occurs for this class of matters, we have, of course, that the determinant of F is equal to 1. And for example, if we consider single uniaxial stretch, we get the standard stress-strain relation, which is typical for neo-Euclidean materials. So we have nonlinear relationship between the stretch and the stress that we measure in the material. So let's move to the model that can describe how this matter fails under tension, for example. We consider the variation of the distribution of the chain length. So we start from the initial state, phi naught here. We consider to stretch the material, and this has the effect to change the shape of this distribution. So we have, for example, an originally chain with length r, which is more stretched, so it increases length, while the opposite occurs on the other side. We are considering a vector, so we have positive and negative vectors, let's say. And we can say that we can have failure, for example, if our chain reaches a length which is above a given r star length that we define later, and then can give rise to the break of the chain, so this chain does not contribute anymore to the energy of the system. So the total variation of the distribution function can be written by using a first part, which is related to the cross-link existing in the material. We don't take into account this term here because we don't consider, for example, degradation of the material, but only the variation due to the deformation that we are applying to the material. So delta phi f is the only contribution that we are considering in this model, but we can also add more contribution in the case we have this aspect. So our variation is written in this way. So we neglect the first part, and that we before we consider this variation that consider that the chain, the single chain, fails when we reach a maximum length, which is called r star, which is equal to nb, so n times the length of each single segment. So when the chain is straight, we can say that it can break and so it does not contribute anymore to the energy of the system. Finally, if we want to get the stress, for example, from standard fine elasticity theory, we can get the pure stress by deriving the mechanical energy with respect to the deformation tensor. We can get the complete expression, which is again an integral over the chain end-to-end distance vector r. And finally, if we want to have the Cauchy stress or the green strain, we can easily found it by using the pure stress obtained this way. To verify our model, we try to testify some samples made of very soft polymer, which is called Sealguard. It's a kind of silicon. We consider several plates with different initial defects, blunt, mild notches, and straight crack. We have here the radius curvature at the notch tip and the stress concentration factor evaluated by using standard formulas. And we try to calculate, to determine the load displacement curve as well as the strain distribution inside the specimen by using digital image correlation techniques. So we measure precisely what is occurring in the material close to the notch tip. We have the case of the blunt notch, of the mild notch, and of the perfect crack, straight crack here. And as you can observe, the deformation is very similar, irrespectively of the initial defect that is present in the structure. So we have from 12 to about 60 as a stress concentration factor for these two cases here, while we have the crack in this case. These are the DIC images coming from the experiments for the three different kinds of initial defects for an applied strain equal to 80 and 31%. And as you can observe, they are quite similar. So the effect of the initial defect is really low in this class of materials. And just before failure, for example, we are at incipient failure here. You can observe that, for example, in the case of the crack, we can even reach a greater value of the applied strain than in the case of the blunt notch. So, of course, there are some uncertainties in the experiments, but this trend is normally quite common to find in laboratory tests. Here I have a video showing what happened. This is for the first specimen with the blunt notch. The KT is equal about 12. Okay. It should start. No. Okay. Of course, this is an accelerated movie of what is happening. The test took about 20 minutes. This is the second test for the mild notch, and the last one is for the straight crack. And we have a behavior which is more or less similar to the previous ones. So we have here the crack pattern that we obtained for the different specimen. We reach almost the same final strain at the failure. So the initial defect is really unimportant in these cases because we have this local failure of chains close to the crack tip, while after, let's say, a local failure, we have a behavior which is almost independent of the defect that we have initially in the specimen. And finally, here I compare the result from the DIC measurement to those coming from the continuum model I showed before that has been implemented in a finite element model, in nonlinear finite element code. And you can see the comparison of the strain, of the green strain, for the three different cases of blunt, mild, and perfect crack at a given level, of course, of remote strain. So let's move to some conclusion. We have considered the problem of defect tolerance in highly deformable materials, such as rubbers and polymers, we have tried to verify this capability of this material to withstand with defects, both from experimental and theoretical point of view. And we developed a model based on the rubber elasticity theory that can explain how locally the material fails under large strain. As we have seen, the ability of this material is to smooth out the peak stress, and so the initial defect loses its character to decrease the strength of the material. So the micro damage that occurs in the polymeric chain can explain what is happening in the material at the macro level, and finally we can use this model to describe very wide class of materials. Of course, they are all soft matter, such as rubber, gels, biological tissues, liquid crystal, and so on. So it has a wide applicability, and we cannot use standard mechanics to explain how this material behaves.